reading you just did, you saw a little bit about how information is stored in binary in the computer. One of the most important concepts that I hope you came away with from that reading is this right here, that a single byte can represent many different kinds of data, and what data it actually represents depends on how the computer uses the byte. This is a really fundamental concept in computer science. In MATLAB, we've talked about how variables have types, and how these types are then going to influence how we interpret the sequences of bytes and bits that we store, right? So what we're doing when we make a variable, right, is that we're attaching a type to it so that we know how to interpret the bytes that we store and also how much space we need to store that value. So for example, we saw there are different types of integers. So there's int 8, int 16. That number that it's attached to tells us how many bits we need to store that value. And while everything is represented in bits, we're actually going to store it in byte-sized chunks. So memory is addressed by the byte. The smallest unit you can set aside to store a value is a byte. So when we use some variables in MATLAB, let's say we have these two integers. Again, memory is addressed in bytes, and so we use the type that we're attaching to the variable to tell us how many bytes we need for that variable. So here, I have an int 8. Right? 8 bits is 1 byte, so that means I need to go to memory and find 1 free byte to store my value. I'm going to set aside the byte and say I'm storing the variable num1 here, and the value of num1 is 15. Then down here, I have an int 16. 16 bits is 2 bytes, so I need to find 2 consecutive bytes somewhere in memory to set aside. I'll set them aside and say this is going to be the variable num2, and the value that's contained in num2 is 9. And you can see that down here, if I do whos after I've used both these variables, that num1 takes up 1 byte and num2 takes up 2 bytes in memory. So this is how the type of variable can impact how much space we need to store that variable in memory. Right? It also tells us how many bytes that we're going to access every time we access that variable, and it tells us a little bit about how to interpret the value that we get when we access that location in memory. So this location memory, I'm going to interpret the binary that's stored there as an integer, and same here, it's going to be an integer. It's just stored in more bits in memory. Notice that even if I'm not needing all 16 bits, so I don't need 16 bits to store the value 9, I'm still going to set aside 2 whole bytes because that's the convention that we've agreed on for this data type. All right, so we know we're not actually storing 15 and 9. We know that we're storing binary. Right? And so what's actually going to get stored in memory is a sequence of bits, and then we just have to look at how we're going to interpret those bits. So to understand how we're going to interpret a sequence of bits, let's take a step back and look at how we interpret a sequence of integers in sort of everyday life in math class. Right? So the numbers that we're used to dealing with are actually in base 10 or decimal. Right? And in a numerical base, right, you have a sequence of digits, each of which is weighted by its place. And so in base 10, you've probably heard of these places. This is probably throwback to about 3rd grade, right? We have the ones place, so the place with the least weight is on the right-hand side. And then as we move to the left, the places go up in weight by a factor of the base. So the next spot over is the tens, and then the hundreds, and then the thousands. So we start on the rightmost with the exponent 0, right? Is the weight that we give to that location. So it's 10, which is the base to the 0 power. That's how we get the ones place. Then we move over 10 to the 1st power, right? That's how we get the tens place. And then get the hundreds place, it's 10 to the 2nd power, right? So then whatever digit is in each of those places gets weighted, right, by its location in the number. Another thing that's important to think about when we talk about a base is what are the values that can go into each of the digits. The range of values is always going to be from 0 to the base minus 1. So for example, in base 10, the possible values that can be in each of the places, they go from 0 to 10 minus 1, or from 0 to 9. In binary, which is base 2, we only have 0 and 1, right? But it's 0 to 2 minus 1, or 0 to 1. So each spot can only be a 1 or a 0. To get the total value of this decimal number, we can just add up each of the places. So to get the contribution of the 1, we multiply it by its weight in the number, by 10 to the 2nd power. Then we add 3 times its weight, which is 10 to the first, plus 0 times its weight, which is 10 to the 0. And then we add those all up, and we would get that this is 130 in decimal. In binary, right, if we want to interpret a sequence of bits as an integer, right, which is what we were doing before. We were saying that that int 8 that we store, we're going to interpret whatever bits we store in that variable as an integer. We can do the same thing, right, but instead of adding up base 10 weights, we'll add up base 2 weights. So in binary, the places in a number are weighted by powers of 2. Again, we start on the right with the least weight, which is 2 to the 0 power, then 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and so on. So instead of 1s, 10s, 100s, we have 1s, 2s, 4s, 8s, and 16s. And then we just add up the weights of each of those places to get the total binary decimal equivalent of the binary number. So sort of shortcut 2 in binary is that it's always going to be 1 or 0, and you don't really have to worry about the zeros because it's always going to be 0 times whatever the weight is there. So the sort of shortcut is to just add the places that have a 1. So we would add 16 plus 8 plus 1 to get the decimal value. And we can see that 11001 in base 2 is equivalent to 25 in base 10. And we'll see a couple more examples, but this shows us how we can interpret this sequence of bits right here as a decimal integer.